In this lecture, we're going to talk about performance. So we're going to look at different algorithms, and I'm going to show you some techniques for how we can analyze their performance. And so first, we'll motivate it by I'll tell you why we care, what kind of important problems we might want to solve, and how the performance of the algorithms we develop to solve those problems can have a major influence on the sort of problems we can solve. We'll talk a bit about how functions grow, and so there's a graph here. We'll talk more about that in a little bit. And while there is a formal method for doing this sort of analysis of algorithms, here we're going to take a very empirical approach using something called the doubling hypothesis. So we're going to run our programs, measure how long they take, and see their order of growth empirically, which is often a very handy technique when you're out there making your own software, so you can understand like what's taking the most time and how big of a data file you can actually run your program on. And the challenge here is, how long is your program going to run? You start your program and it's running, and it hasn't finished yet, and it's taken a minute, and you think, well, am I going to wait a minute, or am I going to wait an hour, or am I going to wait a year? How big of a problem can I solve with a particular program? And what we're going to use here is the scientific method to understand the performance. And we're going to observe things about how our algorithms work. We'll hypothesize a model that's consistent with those observations, and then we can actually make predictions using that hypothesis and verify them, and so on. And important parts of the scientific method is experiments should be reproducible, and in some of the empirical stuff we'll do, there'll be some variability. And your computer is doing many things, right? It's not just running your program. It's checking for Windows updates. It's virus checking. It's pulling email and so on. So it's got a lot of pans in the fire, so to speak. So everything won't be completely consistent, but if you run things multiple times, you should get some fairly consistent results. And the hypotheses we come up with should also be falsifiable, so we should be able to prove that they're not true. As I said, we want to do performance analysis. We'd like to know when the program is going to finish. If it's taken a long time, when is it going to finish? And even further, will it ever finish? Okay, you can easily you might be surprised to learn, but it's easy to take a state-of-the-art modern computer with the fanciest processor and the most memory, and you can easily create a very short program that will take longer than the age of the universe to complete. It's actually surprisingly easy to do this. And another reason we want to study performance analysis is often there are more than one way to skin a cat. You're trying to solve some particular problem. Say you're trying to sort, a big array of integers, and you've got different techniques in which is better. And should you care, if the differences, you want to be able to compare the different ways to sort those integers and see, is it really worth the trouble to do something more complicated? How much time is it going to save you for the problem sizes you're actually working on? And finally, why we care about performance analysis: by finding better algorithms, they might be more complicated, but if they bias enough performance-wise, they may enable us to build new things and to research things that we were previously unable to look into. Here are a couple examples. Sorting is a very common problem in computer science. It crops up all the time. You've got a bunch of items and you need to sort them in an ascending order or descending order, and in what you're exactly sorting, and maybe it's integers, or maybe it's floating points, or maybe it's color objects, or anything that has some sort of order. We often want to sort them because we've seen there are algorithms like binary search that require we can find something in a big list quite quickly, but it needs to be a sorted list. And so how do we sort that list? And we've seen, algorithms. We've already talked about merge sort, right? And that's a fairly recent algorithmic success. 1945. It does its job if we have n. So whenever we talk about performance analysis, we always talk about n, which is the size of problem you're trying to solve. And in sorting, it's the number of items you're trying to sort. Using our friend merge sort, we can do this in n times the log of n. All right. If we do some other kind of simpler, maybe a simpler to code up sorting algorithm, it's going to take n squared steps. All right. It may not seem, there's two n's here and there's an n here and an n here, but this log makes a very big difference. Okay, the log of n, the log of even a really, really, really big n is really not that big. So you're hitting this n on the left side with something that's just not nearly as big as hitting it with another n. And this graph shows you actually the difference. Quadratic would be the n squared algorithm, whereas the linear arithmetic is another word for n log n. And you can see, you can hardly tell. Linear would be just something that goes as n. So instead of taking n squared steps, it takes just n steps. So that's linear. And linear arithmetic, yes, it's above, but as we're doubling the problem size, it's really not that far off linear, and it's a heck of a lot better than quadratic. And sorting is it's just everywhere. The databases, all the major, the search engines and major online merchants and so on, they have big lists of stuff, and they all need to be sorted. And if they didn't have an n log n sorting algorithm, they might not be able to sort the amount of data they have. Here's another problem, discrete Fourier transform, and you're basically doing some analysis on waveforms and breaking them into the various components. And if you do this kind of in a naive way, in a brute force way, it takes n squared steps. And there's an algorithm called the fast Fourier transform, and the FFT, and that again is kind of like merge sort. It's gone down from n squared to n log n, and this has enabled all kinds of modern things you take for granted, like DVD players and iPods and so on. It might not seem like much, but going down to n log n enables things to be done that would have not been possible if we only had an n squared algorithm. From physics, one thing sometimes they want to do is simulate gravitational interactions between different bodies. This is called an n-body simulation. You might do it, as far as planets go. You might simulate the motion of all the planets in the solar system. You might do an n-body simulation if you've got a bunch of particles and you're doing a fluid flow simulation. The brute force way of doing this again is n squared steps. You calculate each of the n. So if you've got n particles in your fluid flow simulation, you want to do n squared steps, comparing each one against every other one. And so there's a better way to do this, the Barnes-Hutt algorithm. Andrew Appel, in his senior thesis at Princeton, worked on this. And so basically you can split stuff up and not necessarily compare against all other particles. You can maybe summarize some of the ones that are more distant and basically get an algorithm that takes n log n. And this allows the researchers, be they in cosmology or fluid dynamics, to research things they weren't able to research, or research it at a level of granularity that wasn't possible with the slower algorithm. All right, let's talk about things we might measure. And thus far I've been mostly talking about time, and that's what we're going to look at a lot at, is how long do you have to wait. All right, and we could measure this just using a stopwatch. You could start your program, and click the stopwatch when the program fires up, and then click it when it goes off. And that would, that works, and there'd be a little inaccuracy in the system. We'll use typically use software, just because we're running software anywhere, and your computer can time stuff. And here's the basic Java code. Java, you can obtain the system time in milliseconds at some stuff, and then you do all the stuff you want to do in between, and then get the time in milliseconds, take the difference, and compute the lapse time in seconds. That's one way to do it. as you know, if you get more into software engineering, advanced development environments like Microsoft Visual Studio have performance profiling built in, and you can actually run your whole program. You can run it from end to end, and then once you're done running it, it'll bring a nice report and tell you what's taking how much time, and you can kind of spot your bottlenecks in your code. For the stuff we'll do in this course, we're just going to use a very simple timer like shown in the code on the slide. We may also care about space. All right, and by space I mean, not how much space your computer takes up, how much physical memory the program and the algorithm take up. You don't have an infinite amount of memory. You may have quite a bit. It's often not a constraint in a lot of algorithms you might look at. You can get 8 gigabytes of memory, and that gives you 8.6 billion bytes, where a byte has 256 possibilities. And a double takes 8 bytes, but that still means on a computer with 8 gigabytes of memory, you're able to store over 1 million doubles. All right, and you can even go beyond that, but often it's important to understand, like, if you're using that much space, and your computer can start using your hard drive for memory if necessary, but we're talking orders of magnitude slower, and this will really affect the performance of your algorithm if you start running out of space. And in some cases, when we're looking at algorithm performance, we care about time, and sometimes we care about space. And I've got a little class, Stats Java, that does basic measurement of time, and it also reports some memory statistics from the Java virtual machine. Let's do some performance analysis on a simple problem. It's the 3-sum problem, and you might think it's simple, and there is a very simple way to do this. Okay, and the game is we're going to have so many integers, in this case 8, and what we're going to do is find all combinations, so all ways we can create 3 triples that sum to 0. We can try all combinations, like we could try 30 and negative 30 and negative 20, and that doesn't sum to 0. Or we could try 30 and negative 30 and 0. Well, that does sum to 0. All right, and this will print out the various possibilities. Seems like a simple problem, and you might have guessed, a very simple way to do this is just to loop over all those possibilities, like try pulling this number and combine it with the second number and the third number, and then the first number and the second number and the fourth number and the first and the second and the fifth, and so on, and enumerate all those possible ways you can create those those triples of numbers. Here's the algorithm that does that, and so we're going to read in from standard input. We first read in an integer that tells us how big to make our array. Then we read all the data in the array. Then we have 3 nested for loops. First one goes over all positions of the array. All right. The second one just starts where this guy left off. All right. It starts 1 past that, and then this guy starts 1 past where the J guy is. All right. And so it doesn't actually have to, this guy could start at 0 and this guy could start at 0, but then it would produce duplicates. So basically it's doing what I said, like I starts here, and then J is going to start here, and then K is going to start here, and then K will try here, 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 and here, and then it will advance J by 1, and K will try the remaining positions, and so on. So that will try, because we don't really care about the order we sum them up in. It doesn't matter for addition. Okay, so that's the program we want to run, and let's do some empirical analysis of 3-sum. And I did this on my very first laptop, and so this laptop's from, I don't know, 1996, 1997 or so. It's a Pentium 1, 150 megahertz of pure power, 80 megabytes of RAM. All right, and it still works, runs Windows 2000 Professional. And I compared that with my more modern, it's only, I don't know, a couple years old, maybe 2010, something like that. It's a desktop with 6 cores running, up to 3.6 gigahertz. So this is 150 megahertz. This is 3600 megahertz, right? Did I get that right? Yeah. All right. And 80 megabytes of RAM, 32 gigabytes of RAM. All right. And let's run threesum on those two programs. And so what I did is I ran it on different files of different sizes, from 100 integers to 6400 integers, and I timed how long it took on those two machines. And you can see on the ancient laptop, when we run at 100, it takes 0.33 seconds, and I could hardly measure it on the modern desktop. All right, but notice what happens when I double the size of the input array. Okay, now we're up to 2 seconds, and the desktop's still doing pretty good at 4/100ths of a second. I double it again. Now I'm at 11 seconds, okay, and so on. And by the time I get to 6400 seconds, I mean, I left this run, I don't know, what is that, it's not, it's, most of a day or something like that. This was running for 47,000 seconds. Whereas the desktop, hey, the desktop, I mean, it's a lot newer. It's fast, but what we're worried about here is look how it's going, though. Like, every time I double it, look how much the time is going up. And at 6400, it's still taking my modern fancy desktop 263 seconds to do this for 6400 integers. All right, if I wanted to do it for 64,000 integers, I might be in a bit of a pickle. How do we do the analysis on this? This is the main takeaway from this lecture, is the doubling hypothesis. And you notice when I did that experiment, what I did is I doubled that input size n. I start at some n, and I double it, okay, and then I double it again, and so on, and I measured the time. And here's the desktop data. I started 400, 800, 1600. So every time I double the input size, and I measured the time. Once we have this first two columns of this data, we can compute the third column, which is a ratio. Obviously, not for the first one. What we do is compute the ratio between the time at 800 versus the time at 400. So I took 0.63 divided by 0.16 and got 3.94. Then I did the same thing here, 4.33 divided by 0.63, got to 687, and then the 33.69 divided by 4.433 and got to 778, and then this one divided by this one gave me that. All right, we're dividing to find out, as I doubled n, what happened to the time. And as I doubled from 3200 to 6400, I had almost a factor of 8 increase in the ratio. All right. And the doubling hypothesis means basically we use this ratio to estimate what constant we've got in an expression. We're assuming this performance of our algorithm, the time t, goes as some constant a times n. So n is how big, that's the problem size, that's how big of an array of integers I'm trying to threesum or whatnot, to the power of b. So I want to first find this power of b. How does, is it an n squared algorithm or is it an n algorithm? And depending on which algorithm you get, you're going to get a different ratio. And in this case, I got a ratio that started to get to close to 8. All right? And the way this, it's empirical. It's not perfect data. These numbers aren't all exactly 8. This one's quite a bit less than 8. And it tends to, usually you want to use the numbers that are on the sort of the higher side of, the longer measurements. And it's as close, it's closer to 8 than anything else. So my hypothesis is that b, in this case, is 3. All right, it's a cubic, order n cubed algorithm. Anytime I double the size, I'm going to have a factor 8 increase in the time it takes to get the job done. All right. Now let's estimate that constant. Assuming, and if I do, here's the data from the ancient laptop as well, and again you're seeing the same thing. So in both these cases we get somewhat different numbers, but our hypothesis is the same, is that the algorithm shouldn't really depend on, shouldn't necessarily depend on the how fast of a computer I run it on. The algorithm is still the same algorithm, and this guy is probably n cubed, and this guy's probably n cubed. And now I'm going to estimate the constant. And what I can do is I can plug in a particular time, and I'm going to choose the time for 6400, plug it into the t for the time, okay, equals a, and then I'm going to put in the problem size 6400, and my hypothesis is it's cubed, and then solve for the unknown a. And what we see is we get a different constant for my desktop and a different constant for the laptop. And that makes sense because we would expect this constant to be much smaller, and it is. It's 10 to the minus 9 versus 10 to the minus 7. All right. Whenever we try and calculate a time with the desktop equation, we should get a faster time, right? Because it's a faster machine. And this constant is sort of, rolling up, specifics about the hardware as well as things, how efficient that algorithm is, independent of the hardware. This allows us to make predictions. Once I have the constant a and I know the exponent, I can do thought experiments like, what if on my desktop I tried to do the 3-integer sum problem on 100,000 integers? And I can take the constant, multiply by the problem size cubed, and solve for the number of seconds, and find out it's going to take me 280 hours to solve that problem. Okay, it's like I said, it's very easy to create an algorithm that takes a very long time. And then we can make predictions for the laptop, and it would be a really bad idea to run it on a laptop because now it's going to take over 50,000 hours to compute the 3 sum of 100,000 items. Here's the bottom line: is that's not a very good way to do 3 sum. All right, it doesn't scale to large problems. Like 100,000 is just taking way too long. 15 years of progress, from my ancient laptop to my state-of-the-art desktop, didn't really buy me out of this problem because 280 hours is still pretty long. Okay, I don't really want to wait 280 hours for this program to return. And an n-cubed algorithm isn't so good. If I came up with a slightly more clever algorithm, you can come up with one that uses a bit of sorting and so on and get something that's n squared times log n. And again, this makes a big difference. Log n is much, much smaller than n. And yeah, okay, it's still n squared, but if now I plug in, and I'm assuming the same constant here, which is maybe a bit naughty, but let's it's an estimate of how long it might take. Assuming the constant's the same, I now can plug in my 100,000, square it instead of cube it, take the log of 100,000, or 100,000, and multiply it out, and now it only takes 168 seconds. So that's completely reasonable, and it's the difference between a slightly more complicated algorithm and sort of the brute force naive algorithm. The algorithm does matter. And yeah, I've already said some of this. What influences that constant? Well, the speed of the computer, exactly what you do in your algorithm, details of what's going on in the operating system, the compiler, what Java's up to, and is it clearing out memory with its garbage collector and so on. Things could be happening on your system. These could all influence the constant and give you different values. Here's a graph of different orders, and the doubling hypothesis, isn't perfect. You can't do all analysis of algorithms using the doubling hypothesis. In particular, it's not very sensitive to these logs. Like it really can't very well discriminate something that's n versus n log n. It's not really capable of doing that so well. It's same as between something that's just constant time and something that takes logarithmic time. All right. You can tell basically if you get a doubling ratio where you double the problem size and it doesn't take any longer, well then it's constant, or maybe logarithmic. It doesn't depend that strongly on how big of a problem it is. If you're seeing it double, if you double the problem size and you get a doubling in time, you've got a linear algorithm, okay, or maybe linear arithmetic. If it's going up by a factor of 4, so 2 squared equals 4, then it's probably n squared. If it's 2 to the third or 2 to the 3, you get a doubling of 8, and it's probably n cubed. All right, and if it's going up by 2 to the n, it's bad news bears. The algorithm is going exponential, and this graph shows you sort of and this is a log a log plot of how long it's going to take given for different problem sizes. So we're doubling the problem size on the x-axis, and we're doubling the amount of time it takes on the y-axis. And you can see constant and logarithmic quite good. Linear, arithmetic are hanging out together here. Quadratic, cubic, and then exponential is just stupidly bad. Okay, it doesn't take long. If your algorithm is growing, as an order of growth exponential, it doesn't take long, and you've easily got problems that are too big to solve. And here are the consequences of these different orders of growth. All right, if you have a linear algorithm, okay, you can increase the problem size by a factor of 100. Okay, it takes a few minutes. Linear arithmetic a few minutes. Okay, if you go by a factor, it's going to take several hours. If it's quadratic, cubic, a few weeks, and exponential, it's now going to take forever. Okay, and here, this table on the right shows you sort of what is the impact if suddenly you get a computer that's 10 times faster. How much faster is your thing going to run? Well, if it's linear, it now runs 10 times faster, or 10 times faster for linear arithmetic, 3 to 4 for quadratic, 2 to 3 for cubic. And if you got an exponential algorithm, you can get a faster computer. It's just not going to help much. All right? You're not really going to get done any quicker. That was sort of empirical. You can measure things and make those predictions. You can also sometimes look at the actual code and try and guess what the order of growth might be. There's a small number of functions that describe many algorithms in computer science, and you can see here are some examples of different algorithms. And you get something that's log n usually if you're taking some number and you're halving the problem every time. If you've got this halving behavior, it's easy to get, you easily can get a log n problem. If you just have a loop that loops over n things, that's often an n order n algorithm. If you loop over two loops, so if you've got nested loops and they both go up to something that's about n, then you've got n squared. If you've got 3 nested loops, it's n cubed. And if you got something that looks like this is like a recursive algorithm, and it's making the problem size slightly smaller but calling itself twice. That's probably bad news bears, and it's probably an exponential algorithm. If you're having the problem and calling yourself on things that are half as big, something like merge sort, then that's often an n log n. So sometimes you can just kind of look at the code and make a good guess at what the order of growth might be. But sometimes this is, could trip you up. Nested loops are, as I said, a good clue. So if you have one loop that goes up to n, it's probably n. If you have 2 nested, it's n squared. If you have 3 nested, it's probably n cubed. But make sure the loop must go on the order of n times. So going n over 2 is the same as it's on the order of n. All right. So some constant factor of n. If you multiply n by some like 1/2 or 1 divide it by 100 or something, it's still on the order of that n for large n. If it's not a function of n, then it doesn't cause that to happen. And here are 2 examples of that. Here's a triply nested thing, and each of these goes from 0 up to n. So this is for sure going to be a n cubed order of growth. And here's the empirical numbers from that, and you see, you get a very good ratio of 8. So 2 to the 3 is 8, and it's a n cubed algorithm. Whereas, what if I do this? I change that inner loop, and now I just go up to 10,000 instead of n. All right, 10,000 is still a lot, and it seems like, you could look at the one on the right and say, well, that's even worse, but it's not. For large n, okay, n's that are, bigger than 10,000, this is starting to be to our advantage. Once n is over 20,000 or more, we're starting to win. All right, because we're having to do not as much in that inner loop than the guy on the left has to do. And you can do that empirically, and you can actually see you get a ratio that goes to 4, and so that's an n squared order of growth. Alright, and here are those two examples, I guess, again. Let's look at a third one. What if I did n over 5? And well, that's better, and it is better. Okay, it is faster than the one above it, but its order of growth is unaffected. For large n, this is still an n cubed algorithm. It's just that you've lowered your constant. So notice the a has gone down to 10 to the minus 7 instead of 10 to the minus 6. It's an advantage to do less in that inner loop, but it doesn't get you out of the fact that it's n cubed. And so if I crank up this n high enough, I'm still going to have the bad order growth of a cubic algorithm. Whereas if I really crank that k down, and now it's a constant, all right, I haven't made it worse. Okay, it's the same, it's still n squared, and I've just made, this is better. I mean, it's better to do 10 things than 10,000, right? And so you can see the constant went down by quite a bit, and my times went down by quite a bit, so now I can do this a lot faster. But if I crank up the n high enough, it's still n squared, so eventually I could still make this algorithm, this program in the computer come to its knees. I just need a big enough n. Alright, and here's another example of, it's not always as clear cut. Alright, so don't think it's necessarily clear cut. You can just look at this code and say, oh well, this is clearly order growth n, because we've got one loop. Alright, there's only one loop, and it goes from 0 up to the length, and so as a function of the length of this string, this is an order n algorithm. Is that true? Well, not in the case of Java, as we'll see. Okay, and so this is a simple string processing function. It just goes through all the characters, finds anything that's what is it looking for? Things that aren't numbers. Okay, and gets rid of them. All right. Here is what happens when you run this program, though. You run it for different length strings from 8 up to 512, and you can see the times. Okay, we're getting a ratio that's around 4. Okay, so 2 to the 2, and that suggests we have an n squared order of growth. But look at the code, like it's only got this one inner loop. Where's this other inner loop? It's only going over the characters once. So why would it take longer than just the n characters? Why isn't this a linear algorithm? And this brings us to this is an important point, and you got to be a little careful about string objects in Java, in that they're immutable. They can't be changed in any way. Anytime you do anything with a string, you're creating a whole new string and copying the old one. And while this result plus equals ch looks fairly innocuous, it's actually fairly expensive. What it's doing is every time it adds one character to that result variable, it has to take that old result variable, copy all the letters in it, add the new one on the end, and then throw away the old one. And that's quite expensive, and there's essentially like a hidden for loop inside of that result plus equals that actually going through and looping through all the characters and copy them all. So there's really a secret loop in there. And so here's how you could fix it if you want to do this fast in Java. Instead of using the string class, there's another class called the string builder. And the string builder isn't immutable. You're allowed to change it, and so this allows it to be a lot more efficient in this particular circumstance. We create the string builder, all right, and it's a reference type, so we create it with a new operator, and then we just call the append method instead of the plus equals. And this doesn't have that deficiency. It just adds on to the end without having to copy the rest of it. It just keeps chunking new characters on the end, and it doesn't have to do the copying, and it doesn't have to throw away the old answer. And this makes a massive difference. If you run that original version that's using the built-in Java, or the Java string, the mutable strings, here is the performance analysis, and as I showed before, it's going as n squared. Whereas if I put this in a string buffer, I can't even really measure. I mean, I had to crank it up to a stupidly sized string, because this is now a linear algorithm, and it's just fast. And so be careful of this, because these numbers, these strings aren't that big. You could easily in a job someday create some string processing code that could really slow down your users, and they might notice the lag in your system, and it's because you've done something like this. All right, so if you'd use a string builder, you could do it a lot faster. All right, to summarize what we talked about today, we looked at very quick and fast introduction to analysis of algorithms, and we mostly focused on doing this empirically. So measuring things, making a hypothesis about the order of growth, estimating the constant, and then using that so we can actually make predictions about how long your program is going to take to complete. And this is just one lecture. There are you can take an entire course in the analysis of algorithms, and that will tell you how to determine some of the nuances, like is it linear or is it linear-arithmic, and so on. You've got to do some more formal, some more math to figure out things like that. But what I want you to come away with is an appreciation that the algorithm, exactly how you do something, does matter. You just can't, even if you have a fast computer, you just can't just do things however you want, because if you do things with an algorithm that has a bad order of growth, you can easily create situations where your program is just never going to terminate. It's just going to work forever on something. And practically, I showed you an important point about that. You can't always sometimes you can look at the code and determine the order of growth. Other times you got to be a little careful and understand what's going on under the covers, like in particular with strings. Be careful if you're constantly appending to a string and you're doing it quite a lot inside an inner loop of an algorithm. It could really affect the order of growth of your algorithm. And then finally, the main takeaway on this lecture is also the doubling hypothesis. And so you should be familiar with this procedure. You double the size, you time it, and then you compute this ratio, and the ratio gives you this exponent b, and then you can just plug in and do some algebra to solve for the constant a.